Okay, let's start. So before we start, actually you can find this. Today we are going to have a quick recap of what we have learned in this term. And before we start, actually, if you look at the page on WebCMS for the slides, you will see this. But this is not an error. Actually, it's just because Prezi.com doesn't allow their web page to be like embedded in. Yeah, I try. Yeah, so it's not an error of the web page. It's actually because Prezi.com actually doesn't allow people to embed their web pages in iframes. So what you can do is you can just click on this view in browser to view the slides here. So as you can see here, this is like a knowledge graph, literally a graph for what we have learned through this term. And different color actually have different meanings. Like for the red color is like the basic introduction of the basic concepts. And the blue ones are the basic techniques like black box testing, white box testing, and different levels of testing. So these are the basic concepts for the most basic types of testing techniques. And the two purple colored ones are actually two practical system testing techniques. And all the green colored ones are all the concepts related to testing. And the yellow one, or the gold one, is actually the advanced algorithms for doing testing, which can be used to enhance the different testing techniques. So let's go through them in detail. So today I won't go through the like concepts because we have learned it in um, those individual lectures. Instead, I will try to make you rethink what we have learned and see if you can still remember the concepts. And before we start, actually I added some annotations to this page to denote the understanding level needed for the final exam. So actually there are 4 levels. So the first one is you just need to know, okay, there is such a thing. So you just need to know the concept. And the second level is that you are expected to be able to explain why this concept works and how it works. And the third one is that you should be able to use the concept to solve some practical problems. And the last one is that you are kind of like required to write or fix some code related to the concept. So that's the first concepts. And let's start. So at the very beginning of this term, we have actually learned the introduction to software testing. And we started from the concept of software dependability. So what we want is that we want to eventually build dependable software. And software dependability is actually made up of 4 different properties here. These 4 properties are correctness, reliability, safety, and robustness. And for these concepts, you should be able to explain them, like, for example, what is the difference between safety and robustness? What's the difference between reliability and correctness, right? You should be able to explain them, not just to know, okay, these are the 4 concepts. You should be able to understand them. And then we also learned verification and validation. So in short, verification is about, are we building the product right? So it's more about the process of building the product. And validation is like, are we building the right product, which is more about whether the final product meets the need of the customers. And we know that software testing is considered as a validation technique. And for this, you also need to be able to explain the differences between verification and validation. And then we also learned dynamic versus static. So we know that testing is actually a dynamic technique because it requires us to execute the target software and observe the behavior of the target software. So it is considered as dynamic. And for static analysis, it's more about like having the source code or the artifact of the software static there, and then we scan through the artifacts to look for some patterns. And for this, you also need to be able to like briefly explain why testing is like considered as dynamic. And then we learned 6 basic principles for software quality assurance. And these principles actually are, we have echoed some of these principles when we learn new techniques. For example, when we learn a dry sanitizer, we know that it's kind of like improving the sensitivity of testing, right? And for these basic principles, you just need to know that they are there, so you don't need to like memorize like all of them. So you just need to know that, okay, there are such things. So that's all for the introduction to software testing. And then we started to learn some functional testing or black box testing technique. For functional testing or black box testing techniques, because we are treating the target software as a black box, we don't have knowledge about what's happening inside the software. What we can only do is we can control the inputs, right? So all the strategies here are kind of like related to how do we divide the input space. And we have many different approaches for dividing the input space. For example, we can use some boundary values to divide the input space. And for boundary values, we have 2 different like assumptions. The first one is like whether do we assume that there's whether do we allow the values to be like out of the range, right? And this is related to normal boundary value testing or robust boundary value testing. And the second thing is about whether do we assume that there is only one value could take the wrong, like the faulty value or not, right? If we allow more than one parameters to take or inputs to take a faulty value, then we are breaking the single fault assumption and we are doing worst case testing. So these are the different types of boundary value testing. And for this boundary value testing, you are required to be able to use it. So you should understand, okay, there is this concept, you should understand how it works, and you should be able to apply it to solve some problems. And then we also learned about using equivalence classes to divide the input space. And similar to the boundary value testing, we also have 2 assumptions here. The first one is like still related to normal versus robust, which means whether do we allow values to be invalid or not. And we also have weak and strong, which means whether do we want permutations or combinations of different equivalence classes. And for equivalence class testing, you are also required to use it, to be able to use it. So to use equivalence class testing to solve problems, to design test cases. And then we learned another approach for dividing the input space according to the relationship between inputs and outputs. And this is called decision table. So you should be able to identify like what is a step of a decision table and what are the entries of a decision table. So steps are like table headers, right? And entries are the actual values. And you should be able to identify the actions and conditions of the decision table. So the conditions are more like the program inputs, and the action are kind of like the program outputs. And you should also be able to know that the differences between limited entry decision table and extended entry decision table. So for limited entry decision table, we only allow the values to take true or false, to take binary options. But for extended entry decision tables, we allow the table entries to take non-binary values. So for decision table, you should also be able to use it, not just like understanding these basic concepts, but you should be able to apply these concepts and use it.
It's like one question in assignment one,
Uh-huh.
where we had to like choose the right decision table.
Mhm.
Or was that assignment two?
It's assignment 2, I think.
Assignment two.
Yeah. So that's kind of like an application level of question. So that's all about functional testing. And then we started to learn structural testing. So structural testing is also known as white box testing. So we have access to the source code of the program. And structural testing, because we have access to the source code of the program, we can count our test coverage. And structural testing is all about using like different coverage metrics. And we started from the simplest coverage, which is statement coverage. So the requirement of achieving 100% of statement coverage is to just execute all the statements of a program. And for this one, you should be able to use it. But this is very straightforward, so it's not a big issue here. And then we learned branch coverage. And before we learn this branch, we should know where is a branch. So the branches are actually inside a graph, which is known as control flow graph. So you should be able to build a control flow graph given a piece of code. And we can find some branches inside the graph, right? Where a node have like 2 outgoing edges, then there's a branch. So the target of branch coverage is to execute all the possible branches by taking both true and false branch of each, true and false edges of each branch. And for branch coverage, you should also be able to like use it. And then we learn condition coverage. Condition coverage is like, and because branches are normally related to conditions, like if the condition is true, then we take the true branch. If the condition is false, then we take the false branch. But there are some cases where we can have conditions without branches. For example, we can assign Boolean values using these the result of the calculation of these conditions. And in that case, we know that condition coverage actually subsumes branch coverage. And we also learned this modified condition decision coverage, which is known as MCDC. And there are different levels of MCDC, and it's actually also part of the requirement of the NASA coding quality assurance guidelines. And for condition coverage, we don't require you to like memorize all the different concepts here. You just need to know, okay, there is such a thing, so you don't need to like get very deep into these concepts here. And then we learn path coverage. So because we have the control flow graph, actually we can extract path from this graph, right? By connecting different nodes with different edges, we can extract path. And for path coverage, there is a very infamous phenomenon known as path explosion, because whenever we reach a new loop, we loop one more time inside the loop, we have a new path. Whenever we reach a branch, the number of paths doubles. So there's a problem called path explosion. So normally we cannot achieve 100% of path coverage because there could be a very large number of paths of a program. So that's why we need to have some simplified or weaker version of path coverage. The first one is boundary interior coverage. You should know, okay, what is like boundary interior coverage, right? And we can also do the simplification by bounding the number of times we enter certain loops, and then we can get loop boundary coverage. So you should be able to know what are the interesting values for these like loop boundary coverage. And then we also learned LCSAJ, which is an advanced version of path coverage. We can adjust different levels of LCSAJ to achieve different levels of complexity for counting the coverage. And lastly, we know that even if we can achieve 100% of path coverage, a program may not be free from bugs because we didn't care about how do we execute the path. We don't care about the value used for executing the path. If we just check the path on the control flow graph. And for the concepts of path coverage, most of them are like on level 3, so you should be able to use these coverage metrics, except for LCSAJ, which you just need to know this concept here. You don't need to be able to like apply different levels, because LCSAJ is normally like requires you to build an interprocedural control flow graph, which could be very large and tedious. So we don't require you to use it. You just need to know, okay, there is such a concept. And because 100% of path coverage is not enough to reveal all the bugs, because we are only dealing with the control flows, right? So we need to deal with data flow as well. And we briefly learned about some concepts in data flow, in the tracking of data flow. And the key of data flow tracking is about checking all the diffuse pairs. And for this part, you should be able to explain it like what is a diffuse path and what is like a diffuse pair. So, and given like a piece of program, you should be able to identify like all the definitions of a variable and all the usages of that variable. So this is all about structural testing. And we can see that we learned it in this direction, because in the direction of increasing like testing costs, like we are starting from the simplest type of coverage and towards the most complex or most comprehensive type of coverage. So this is structural testing, and both structural testing and functional testing, they are actually benefiting the different levels of testing. And different levels of testing is actually, and actually both functional testing and structural testing cares more about how do we create test cases. And different levels of testing actually deals with what target do we test. And the different level of testing actually is mostly based on this V model of testing, which is a combination of software development lifecycle and software testing lifecycle. And we can see that we have different levels of testing here, and each level is actually related to a stage of software development. And the first level we learned is unit testing. And we know that it's normally done by the developers. And it's actually the basis of test-driven development. And a unit test could be either black box or white box, depending on what kind of development style are we doing. For example, if we do test-driven development, then it's more like a black box testing because we are writing the tests before we write the code. And if we already have written the code and then we write unit tests, then it's more like white box testing. And for unit testing, you should be able to explain the different concepts here. And then we move on to the integration level of testing. And for integration testing, normally it's done by the internal testing team. If the company is big enough to have different teams. So integration testing is to combine different units together to test them together. So it's all about how do we combine these different units, right? And we can have several different approaches here. So if we just have the requirements, what we can do is we can do decomposition-based integration by decomposing the requirement tree. And we can do top-down integration, we can do bottom-up integration. And if we do top-down integration, we are required to implement some stubs of the features. And if we do bottom-up integration, we may need to implement some drivers to simulate the higher level of program units. And we can also do sandwich and big bang integration as well. And if we have the source code of the program, what we can do is we can get the integration of different components from the call graph. And the call graph is a special type of control flow graph where each node is a function and each edge denotes whether a function is invoking another function or not. So we can extract components from this call graph here, and we can have different types of integrations. For example, we can do pairwise integration by combining all the pairs of functions on the call graph, and we can also try to do neighborhood integration, which is to define the size of the neighborhood and build neighborhoods as integrated components. And lastly, we can also try to do some path-based integration. And for the integration testing, you are also required to know not only the concepts, but also try to explain what are the differences between each type of integration. And then we learned the uppermost level of testing, which is known as system testing. So we know that there are model-based testing, a typical type of model is decision table. And there are also other different types of models, like context-free grammar, like finite state machine, and so on. And we also learned that for system testing, we can do non-functional testing to test other properties of the program, like the performance, like the usability, compatibility, or even sometimes accessibility. And for system level of testing, because there are so many concepts, we can't drill very deep in every one of them. So what we want you to achieve is just to know there are such techniques. We don't need to be able to explain them, but you just need to know that there are these techniques. And then we learn about test scaffolding, which is related to how we build different. This is like a typical template for us to build like any unit or integration testings, test cases. So you should be, given this template, you should be able to apply it. For example, given an actual piece of code, you should be able to identify which part is a driver, which part is a stub, and like you should also be able to identify the output comparison and tear down code. So this is test scaffolding. And the key here is about the differences between drivers and stubs, right? So you should be able to know the difference between these two concepts. And that's all about different levels of testing. And then we started to learn some actual system, because we just briefly go through all the system level system testing techniques, and we picked two specific system testing techniques to learn them in detail. And the first one is fuzz testing, and there are different colors of boxes for fuzz testing. And the first one is black box fuzzing. So you should be able to know that there are like mutation-based fuzz testing or generation-based testing. You should be able to explain the concepts. So like what is the difference between mutation-based fuzzing and generation-based fuzzing? And like what is the key rationale of fuzzing? We know there is such a concept called infinite monkey theorem, right? So it's basically to use very large amount of random inputs to trigger like all the potential abnormal behaviors of the program. So that's the key rationale of fuzzing. And then we also learned about white box fuzzing, which is normally known as symbolic execution. And because symbolic execution suffers from the path explosion issue, we sometimes, in practice, we do concurrent execution to combine concrete execution and symbolic execution together. And for this part, because the concept is very, I think there are some flaws with the notation of the understanding level requirement here, but you can see the color here. So this is level 1. So you just need to know that there are like such concepts known as symbolic execution and concurrent execution. You don't need to really drill deep into these directions. And because black box testing is not very effective, and white box testing is normally not very scalable, so we try to combine these two together to get gray box testing or gray box fuzzing. So you should be able to know the key mechanism of gray box fuzzing. So gray box fuzzing is actually to here the gray box means we are still collecting execution or runtime information, but we don't collect every piece of information. We collect only the information needed for testing. And you should be able to remember why it works, because it's kind of like exploring the program's states using a divide and conquer approach by keeping some interesting seeds and generate new test cases according to the seeds we have kept. So this is the key mechanism of gray box fuzzing. And then there are several strategies related to gray box fuzzing, for example, seed scheduling and seed prioritization and power scheduling and test input generation. And you should be able to like explain like what's the difference between sleep prioritization and power scheduling, like and how what are the typical approaches for generating new test inputs. And then we learned a very special framework called American Fuzzy Love, which is one of the most famous framework, a gray box fuzzing framework. And you should be, you actually are already practicing some key concepts in assignment 3. So you should be able to like know how it works in practice. So this is all about gray box fuzzing. And you may expect to be able to do some coding here, like not only to use it, but also to write some code, like what you did for assignment 3. And this is all about fast testing. And then we learned about software complexity. So this is like one of the concepts related to testing. We learn it because there is an assumption that if a piece of software is more complex, then it is more likely to be buggy. So that's why we are interested in measuring software complexity. And here we learned several different levels of software complexity. First, we learned the unit level of complexity. We learned two different set of metrics here. The first one is cyclomatic complexity. We know that given any graph, we can calculate the cyclomatic complexity, right? Using the formula E, number of edges, yeah, minus the number of nodes plus 2, right? And because actually the most precise one is 2 times the number of subgraphs. But here, because we are doing unit level of counting, there's only one subgraph for each function. So it's like E minus N plus 2. And there is an approach for doing fast calculation of cyclomatic complexity without the need of building uh, a control flow graph, because sometimes it's kind of like tedious to build a control flow graph. We can calculate cyclomatic complexity by counting the number of some special statements, like the if statements, like the loop statements, like the switch cases, like the number of returns, right? So you should be able to use these formulas. And then we also learn about house tax metrics, because the limitation of cyclomatic complexity is that it only cares about the structural complexity of the control flow graph, but it doesn't care about the volume of the program. Like a large program which runs securely without like any branches may have a very low cyclomatic complexity, but it is still likely to be buggy, right? So that's why we introduce house tax metrics. And there are several like key concepts here. You need to count the unique number of operators. You need to count the unique number of operands. And you need to count the total number of operators and total number of operands to calculate different values here. And for these complexity metrics, you need to be able to apply them, to use them to analyze the complexity of a given piece of software. And then we also have integration level of complexity. So we can have, because cyclomatic complexity could be applied for graphs, and curve graph is also some type of graph, so we can apply cyclomatic complexity for curve graphs as well. And for object-oriented programs, there are some special metrics for calculating the object-oriented complexity. However, these are like kind of very detailed concepts, and we don't require you to like memorize all of them. You just need to know that, okay, there are some special metrics for object-oriented programs. You don't need to know like the exact metrics there. And then we have system level of complexity. System level of complexity is roughly just the same as like integration level of complexity. So you just need to know, okay, there is such a thing. You don't need to like drill deep here. So that's all about software complexity. And then we moved on to test oracles. So test oracles are actually the techniques for telling us whether a test case is a pass or a fail. So there are several different types of oracles. The first one is specified oracles. So most of them are kind of like human created. So we can use model-based oracles. We can use, like for example, we can use finite state machines to check if the program runs into an error state. And we can also try to use some, normally we just use some expected values, right? Like checking whether, like asserting whether the output equals to some expected value or not. And of course, if we are developers, we can also try to inject some assertions into the program when we write the program as self-checks. And when we do testing, we just observe for assertion fields from outside. So these are the different types of specified oracles. And you should be able to apply them, except for this model-based oracle. You should be able to apply expected values and self-checks. And we also have, and because like specified oracles requires some manual effort, what we want is to create some like automated tools. So we can also try to derive test oracles automatically using some approaches. And the first one is we can use differential testing. And I hope you can still remember the concept of differential testing, which is to collect different versions of programs doing the same task. And we can feed them with the same test case, the same test input, and observe for the differences among their outputs. And if they output different things for the same input, then one of them, at least one of them, is wrong. So that's the idea of differential testing. And for regression testing is to just keep a regression test suite to make sure that the introduction of new features doesn't affect the other like existing components. And normally regression testing, you can consider it as a differential testing, like among a newer version of the software and an older version of the software. So this is regression testing. And of course, we can also derive some expected values automatically. And lastly, there's one more advanced technique called metamorphic testing to derive test oracles. And metamorphic testing is more about identifying the metamorphic relation, right? Because sometimes it's very hard to just like to just automatically generate the expected value. And so instead of like comparing the output with an expected value, what we can do is we can try to apply the metamorphic rules to check the correctness of the program. And for this part, you may also expect some coding tasks. So especially for metamorphic testing. And lastly, we learned about implicit oracles. So this is like the most autonomous type of oracles, because these oracles are some behaviors that every program should follow. For example, a program should never crash, right? And we can use some techniques to increase the sensitivity of these oracles. And the typical technique here is address sanitizer. So, uh, although address sanitizer is a very interesting and practical technique, but we don't require you to really know how it works, although we have taught it in the lectures. But you just need to, for the exam, you just need to know, okay, there is such a thing called address sanitizer, which is like, which could be used to improve the sensitivity of the program, to harden the program. And then lastly, we also learned that sometimes we cannot use any programmatic oracles at all. We have to let humans to decide whether the program is correct or not. And in this case, we are kind of like using humans as oracles, and we can do some crowdsourcing to hire some humans to help us to do this. And for this one, you also need to just know, okay, there is such a case. So sometimes we just need humans to work as oracles. And a very typical actually application of this is like human guided model alignment for large language models nowadays. So we want to align the value or the output of the large language models according to like the favor of humans. So in this case, we are kind of like using humans as oracles here. So these are the concepts of test oracles. And then we move to mutation testing. And you should be able to know that mutation testing is different from mutation-based testing. Mutation testing is actually a type of technique used for evaluating the quality of a test suite that is used to evaluate the quality of a set of test cases. And there are some key concepts here. So the key concept is about mutants. So you should know what is a mutant. A mutant is like a variation of the original program by modifying the original program a little bit, right? And this modification is done by the mutation operators, right? And you should also be able to know what is the concept of killing a mutant, what is the concept of a live mutant, and what is how should we calculate the mutation score. And you should also know that we can somehow evaluate the quality of the mutants as well by checking whether they are like useful or not, whether they are like practical or not. Because sometimes when we create a mutant, the program may not even compile or may not even be able to run. So then those mutants are kind of like useless. And for mutation testing, you are kind of expected to do some coding or fix some code or modify some code. So this is mutation testing. And we also learned about when should we stop testing. So when to stop testing is actually related to measuring the reliability of a piece of software, because we know that uh, using testing is kind of like impractical to prove a program is correct. So instead of proving the correctness of a program, what we want is to measure the reliability of the program. And there are several different metrics here for measuring reliability. The first one is probability of failure on demand. And the second one is availability. The third one is like rate of occurrence of fault. And the last one is mean time between failures. So you should be able to remember how to we calculate them, like what are the formulas. Like for example, the probability of failure on demand is like related to how many failures are there in this in a given amount of requests, right? And availability is more about uptime and downtime. And rate of occurrence of fault is like how many faults do we observe during a period of time of observation. And mean time between failure is to calculate the time slot between two failures. And for this measure, for measuring reliability, we require you to be able to use them. So you should be able to calculate these values given some scenarios. And these measurements are actually used in statistical testing. And for statistical testing, we need to collect a user profile to simulate the usage of our software in real world scenarios, like after it's deployed, like how much traffic do we expect? Like how do we expect users to use different features of the software? And according to this user profile, usage profile, we can try to simulate how this software is used in reality, and then we can measure these different metrics to measure reliability, to decide when can we stop testing to release the software. And for statistical testing, you just need to know that there is such a technique. You don't need to really look into how should we collect the usage profile or how do we like set the satisfaction level, right? You don't need to do that. So you just need to know that this is like so these reliability metrics are used for statistical testing. And then we move to combinatorial testing. So combinatorial testing is actually yet another type of system testing, practical system testing technique. So combinatorial testing is all about testing different combinations of the program or different options when we run the program. And because talking about combination, there could be like a very large number of combinations or permutations for us to try out. And it's kind of like impossible to try all of them. So we have to do T-way communication. And T-way communication means that we only care about covering the patterns of permutations of T parameters. And the optimal value of T is normally 1, 2, or 3, right? And if we have a larger value of T, then the bugs we find won't increase a lot. So in order to calculate the and we don't have to, and if we try to achieve like full T-way coverage, we don't have to try out all the possible permutations to cover all the possible patterns among the T parameters. We can calculate a covering array to get the representative values to cover all the possible possible pairs or possible triples of different values of the parameters. And how do we calculate this covering array is actually normally very complicated. And we have learned about how do we calculate this using a greedy algorithm. And here for covering array, you don't need to, for combinatorial testing, you don't need to really know how can we calculate a covering array from zero or from scratch, but instead you should be able to appreciate why covering array can help us to save some efforts. And you should be able to apply covering array in certain sense. So the required understanding level is 3. So you should be able to use covering array for combinatorial testing. And lastly, we learned some advanced algorithms for testing. So basically, we learned how can we model testing as a search or optimization problem, and then if we can model testing as an optimization problem, we can apply genetic algorithm to improve the overall quality of our test suite. And if we can model some problems, some decisions, we make during testing as a multi-arm bandit problem, then we can apply the algorithm of epsilon greedy. So for genetic algorithm, the key is how do we define the fitness function. And for American fuzzy lob of the green box spider, we have learned the fitness function is like whether a seed can cover some new edges or not, right? And for epsilon greedy algorithm, the key is about the value of the epsilon. And if the epsilon value is too large, then we are lacking exploitation. And if the epsilon value is too small, then we are kind of lacking exploration. So the epsilon value should take a suitable value, which is small but not too small. So this is advanced algorithms, and you should be able to use them. And I highly encourage you to look into the two code examples in the slides of our last lecture. And that's all for the recap. And thank you for coming. And I hope that after this term, you should have this. Although we allow you to like bring an A4 page double-sided cheat sheet to the final exam, but I hope that you can have this thing in your mind. So this knowledge graph in your mind, and you can see this is like you can try to memorize it because it's this graph I think is quite structured. So we started from the red color node, which is the introduction, and then we learned some basic concepts of how do we create test cases for black box or white box targets. And we've also learned how we select different levels of targets. And these are the 3 like blue colored basic testing techniques. And we learned 2 purple colored specific system testing techniques. And we also learned several green colored techniques which are related to testing. Like for example, how can we prioritize which part of the software to test according to complexity? Like how should we make our test more sensitive to capture more bugs by improving our test oracles? Or how can we evaluate the quality of our test cases? And of course, when should we stop doing testing to release our software? So these are the knowledge related to testing. And lastly, we also learned some advanced algorithms, which are basically meta-heuristic algorithms, which can help to improve different actual testing techniques. And I hope you can have this in your mind and have and you don't need to, so you don't need to refer to your cheat sheet every time when you see a question, right? So that's all for today's lecture, and that's all for this course for this term. And thank you for taking this course, and thank you for coming today. And that's all. And hope you have a nice preparation for your final exam.
It's
Okay.
like 2 hours long, right?
Yeah, it's 2 hours.
That's
Yeah.
not too bad.
Yeah, I purposefully made it not 3 hours. I have the option to make it 3 hours, but I think it's too long. Yeah.
Questions, did they say or we did?
We haven't decided yet, but we will release the formats later.
Okay. In 2 hours, it's already like not that fast.
Yeah.
Are there any past papers we can do, like past assignments that we should?
No, this is the first term,
Oh,
like for us to do exams. Yeah. And actually, this is the first time for us to use the web page.
there's like no past papers.
Yeah, yes. But you can somehow refer to the assignment questions as like references.
But most of them are just gonna be like in the style of the assignment.
Yes. And
Thank you.
okay, bye.
Bye.